So thank you for the opportunity. So the present session is the present and future of astronomy and space research in India. And I'm going to focus on this subject, sun and its influence on our space environment, national initiatives to study the sun. So here we are at Ujjain. So again, I will start with a little bit of history of solar physics from India. And Madam Annapurni has given a good overview in the morning about the astronomical observation when it started in India. So I thought always we should have the historical perspective also. Why solar physics is important? Sun, Surya Devata is here at an appropriate distance away from us, and we are living at this planet Earth because of the presence of the sun. And why sun is important in our daily life, and also for a longer period of time in terms of our climate. I will try to give a quick glance of that today. So the Madras Observatory was established in 1792 by the British East India Company to promote astronomy, geography, and navigation in India. Just remember these words, why it started. And the science of astrophysics came into being in the 19th century with the introduction of spectroscopy and photography to astronomy in the Western world. So this particular word, spectroscopy, allows it to characterize or diagnose the properties of the emitting medium, whether it is sun, the stars, or galaxies, and so on. So that was very important. And Madam also mentioned about it. Can you minimize this particular frame? My picture is not very important here. Yes, thank you. And the discovery of helium was done during one of the eclipses as well. This is the spectrum which was recorded, and it is there in our Institute of Astrophysics archive, one of the historical archives of the country, where it shows the presence of the helium. And as Annapurni mentioned in the morning, it was first discovered actually in the sun, and sun means Helios, so that's how the name came as helium. We did not know its presence in our planet. So severe famine in the Madras presidency in 1876 to 77 was taken to underline the need for a study of the sun. You see the historical perspective that why solar physics and solar observations came into a very important thing in the British India because of to study the monsoon pattern, which can be better understood. So I'm just trying to again highlight that why solar physics need to be studied for centuries or millennia, because our existence here and our climate's presence is because of the presence of the sun. So it was decided in 1893 to establish a solar physics observatory in Kodaikanal in the Palani Hills of South India, with the Madras astronomer Charles Mickey Smith as the first director. And Kodaikanal Observatory came into existence in April 1, 1899. So that's a bit of a history of Kodaikanal Solar Observatory as of today. So the observatory setup was in Madras, then we moved to Kodaikanal. Then the solar tower tunnel telescope was built, one of the bigger facilities. Then in more recent times, we have additional observing facilities at Kodaikanal. But these are modest facilities. We need actually much more modern facilities. But of course, always you have to remember about the archival value. The history of astronomy and history of solar physics from India and this part of the globe is one of the best actually. And the archival material, what we can preserve, it is actually one of the richest resource for long-term study of the sun. So this is what we have done very recently. But solar facilities, modest solar facilities in India, these are particularly optical facilities. One is there in Nainital, in Aryabhatta Research Institute. You will hear a little bit of the Udaipur Solar Observatory, not very far from here. And then one in the south is in the Kodaikanal Observatory. But that's in optical wavelength. You heard in the morning also, the radio wavelength also gives you, information about any astrophysical objects. Sun is no exception. So we have GMRT facility, which is operating from Maharashtra. Then we have another facility close to Bangalore in Gauribidanur, in Karnataka, Andhra Pradesh, actually in the border. And then TIFR facility from Uti again. So that's major facilities. But modest half-a-meter telescope is also there in Udaipur Solar Observatory. This is a beautiful island at the lake, and with some back-end instruments, we have a half-a-meter kind of telescope, but that's the best what we have today from ground-based observation to look at the sun. This is what I was mentioning, that these archival data from Kodaikanal, we have been looking at the sun for more than 100 years, which has been digitized. And you go to the archive, you will find, if you are born in 1st January 1958, how the sun was looking. So you can actually find that image of the sun in H-alpha, calcium, and white light. These are different filters, images mapping different layers of the atmosphere of the sun in the visible domain. This is one of the best archive in the globe. Take it from me. Why it is important to study the sun? Sun shows change of its magnetic properties. So sun is a magnetic star, and on the surface of the sun, we often find a presence of dark regions. If you take a optical image, those are called sunspots. So sunspots, number of sunspots varies with time. Here, what is plotted here is the number of sunspots for last 400 years. What clearly shows that there are certain periods where there are many sunspots. There are certain time period where there are no sunspots. Can I get back my slide, please? Yeah. So which are also coinciding with a very cold period in the Earth. These are called mini ice age, and this is the picture during this period, in the Europe. 30 years, the Volga River was frozen. Even there was actually another minimum period, we call it Dalton minimum. That time, the Christmas fair was taking place on the Thames River. The river was frozen, so the Christmas fair happened in the river itself. So these are corresponding to the mini ice age. So that means when sun was magnetically less active, then it has direct impact on our climate. So we really need to worry about the long-term variation of the sun. And so here you see there are last 100 years of record. This particular period, the sun was very, very active. There were lots of sunspots and so on. Thankfully, that was the period when we did not have the space era. We did not have space assets. When such big sunspots are present, when such sun is very magnetically active, a lot of very dynamic things happens on the sun. I will show that how important now the sun also is to study in multi-wavelength. This is something in the morning session you have heard from our colleagues, that astronomy has really taken a different leap altogether when we started looking from ground and space. Because until we went to space, we were not able to see the UV light and the shorter wavelength, X-rays and gamma rays and so on. Thankfully, our ozone layer protects us from this short wavelength. So sun looks reasonably, I would say, boring when you are just looking at some days in an optical telescope. There is a small little sunspot here. But if I look at from infrared, which is possible to be seen from very high altitude mountains, this is a UV telescope from space, and this is an X-ray telescope from space. Sun shows much more dynamic, variability and some more structures. So it is almost mandatory to look at the sun in multi-wavelength. And as I was mentioning, the sun is really, really a violent star. Here we are showing a blow-up region, again from one of the NASA satellites, of a region where there are many sunspots. And as you see, a lot of material is confined into these regions. We call them magnetic coronal loops. And when they become unstable, then this huge structure ejects, and a lot of material is actually thrown into the interplanetary space. So we really need to worry about when such huge explosions happens in the sun, and what will be the impact when it reaches Earth. So here I'm showing again you a close-up view from a recent NASA satellite called Parker Solar Probe. When such huge explosion happens near the sun, huge amount of material, we call it coronal mass ejection, is thrown into the interplanetary space. So I think you can immediately make out that this is not a very, very comfortable, pleasant place to be. So if you have a satellite, or if you plan to move around in this particular location, it is not going to be very safe for you. I mean, I can guarantee that your survival is really, really under question. So we need to really now understand when such huge explosion can happen in the sun, and if such explosion happens, how it will travel, whether it is traveling towards Earth or the satellites which are there in our neighborhood and so on. And this particular domain is now called space weather. We need to really know the weather in space. Earlier, we were calling about terrestrial weather. I often give example when I was young, used to go to the coastal side and all that. I will always hear that the fisherman will listen to the radio commentary whether it is safe to go to the fish for catching the fish in the sea, looking at the weather forecast. But today, now all space agencies really call us and find out whether it is safe to launch the satellite. So just not the satellite alone, there are many more assets. There are many more assets in the space, and there are astronaut safety is in question. We are planning our own international space station. Of course, our communications are very much dependent on the ionospheric conditions. So this is a layer in the atmosphere which is responsible for our most of the microwave communication systems and so on. And when such a huge storm happens in the sun, then these ionospheric conditions get changed, and our communication satellites gets into problem. Our radio wave disturbances happen. Electrical grid systems, the transformers, they get affected by the induced current. These charged particles which comes with the storm, they hit the electric grid system, and then that leads to the failure of the of these particular power systems. When a satellite is launched, then the satellite assumes certain atmospheric condition. But when such solar storm happens, you saw from the movie, so much of material is dumped into the interplanetary space. So the normal density, what you think is there in our atmosphere, is completely changed. So that means when a satellite will travel, it will experience a different kind of drag. We call it atmospheric drag. And because of the change of atmospheric drag, satellite will change its trajectory as well. And that's how SpaceX lost 37 odd satellites in just a couple of years back. They were not aware that there was such a storm. It was not a very big storm. It was comparatively a smaller storm, but still it affected the satellite, and it never could reach 400 kilometers, what it was destined for. It experienced a drag, and it came down to 200 kilometers, and it was destroyed. So it is a very, very important area now. We call it space weather. To study the space weather globally, whether you name it NASA, whether you name it JAXA, whether you name it European Space Agency, everybody is, very much aware. There are lots of mission satellites. So what I'm showing here, just for heliophysics system observatory, just to understand the Sun-Earth system. So also I must point out that you can't study these in isolation, because now we understand our Earth is very much coupled with the solar radiation, solar material which is coming. Similarly, the other planets, even if you want to do lunar studies, it is affected by the solar storms. So you have to really study them as a Sun-Earth coupled system. And all these different planetary systems and sun in together, we call them heliophysics. And for heliophysics studies, there are so many active satellites. We did not have anything on our own, but better late than never. We were so lucky, we were so fortunate. We started with a bang. We did not start with a small satellite, we started with a very big satellite. Lagrange 1 mission is one of the sort of leading or challenging mission which only the European Space Agency and the NASA has achieved before us. So we were something, done something before the Chinese could do. So in a way, this is a nation's pride that, we had to catch up with a lot of development. And as you will hear, many of the ISRO's program is something like that we started a bit late, but when we are doing something, we are doing at par with the global standards. So this is really, really a very, proud moment for us. So Aditya is a multi-payload observatory class mission. It has 7 payloads. I will not get into the technical details, but if anybody is interested, I will be very happy to share with you or discuss with you about the different science and the payloads activities. But it is a multi-wavelength covering different atmospheric layers. What happens is the solar surface is at 6,000 Kelvin. You heard about in the morning about the electromagnetic wave. What kind of wave will be dominating the peak and all that depends on the temperature of that plasma ball. So in the atmosphere of the sun, it's actually a mystery that how the atmosphere is much hotter than the surface of the sun. The atmosphere is at millions of Kelvin. So since the atmosphere is in millions of Kelvin, the primary emission is actually in the shorter wavelength, in the extreme ultraviolet, in X-rays and so on. So that means to study the atmosphere, you need to have a capability of optical, infrared and X-rays and, whatever you name it, the shorter wavelength capabilities also you should have. And that is only possible from the space. So now we are really matured, sort of national source to study the different layers of the atmospheric science with solar atmospheric sciences with the combination of 4 remote sensing, and we call it 3 in situ observation. In situ means we are at actually vantage point at Lagrange 1. These solar storms, when they come from the sun, before they reaches Earth, they will pass through Lagrange 1. So that means, sitting at Lagrange 1, we are able to probe the characteristic of these storms, what kind of energy they have, what kind of charges they have, whether they're electrons, whether they're helium, or whether they have magnetic field with that. So those instruments are called in situ instruments. And also from Lagrange, we are looking at the sun with multi-wavelength capacities in near UV, in optical, in X-rays, and doing remote observation. So that's why it is called the remote sensing and in situ observation. So it has
Deepankar, 3 minutes. 3 minutes.
Yeah, I should be done. So that's space-based thing. You heard in the morning. I think we are in a very good phase of astronomy. Of course, we heard we were always very good. You saw from the history that we were fortunate to be able to do topics, astrophysics from this part of world. But today, technology demands, bigger facilities and so on. And now we are catching up. And in India, now we have our own, observatory. And this is the one which we are talking about. We have 4 major astronomy facilities from Ladakh region and 1 planetarium for outreach purpose as well. And this is a project which will have a huge potential. This is a place called, in a village called Melak near the Pangong Lake. And we were fortunate to, set up something here for almost more than a decade. And I spent 3 winters actually in this particular small little location. This is the artist diagram of the current concept or the design. We have the detailed project report for this satellite for this particular telescope. This is going to be really a major facility in globally also. If you look at this table, so these are the major big facilities. Of course, this is in USA. This is currently the largest telescope in Hawaii Island, but this is farther, in the west. East side we don't have. So we have a huge, advantage that when the sun rises first, the Europeans and Americans are still sleeping. So we will have the first opportunity to study the sun. And that's what is projected from a Himalaya. There are 2 other projects also, but the time scales are even larger. So we are trying to catch up with this global, efforts, and I want to have a 2-meter facility, before the others take up. So I think I have been able to give a little glimpse about, why solar physics is important to study its long-term variation and the short-term variation in terms of the solar storms and so on. And we are very fortunate that from India itself, we have facilities which are of international repute. And globally, internationally, people are approaching us, and with a high collaborations, we are planning to take things to the next level. This is a picture taken from our Devasal Observatory in Nainital. You see the Himalayas, the other devtas are all sitting there. So no wonder why astronomers really love to do science, because we get the opportunity to go to these beautiful locations, and that's our Aditya's logo. Thank you for your attention.
Thank you to Professor Deepankar Banerjee. So Deepankar से आपने जाना कि सूर्य कैसे हमारे अंतरिक्ष का पर्यावरण और हमारे पृथ्वी का क्लाइमेट या जलवायु को कैसा इम्पैक्ट करते हैं और हम कैसे इसे स्टडी करते हैं आदित्य L1 मिशन से, और नेशनल लार्ज सोलर टेलीस्कोप जो हमारा नेक्स्ट बड़ा स्टेप होगा सूर्य को स्टडी करने के लिए. नेक्स्ट अप इज़ प्रोफेसर अनिल भारद्वाज. मैं अनिल भारद्वाज को स्टेज में आमंत्रित करता हूँ. Professor Bharadwaj is an expert on planetary sciences. He has had a finger on every space mission that has gone in the last couple of decades to explore any planet in the solar system, starting from the Chandrayaan missions to Mangalyaan. And he's also leading many of the instruments and the vision for the future Chandrayaan missions and planetary science missions. So it's a pleasure that you could spare time to be with us today. So I would like Professor Bharadwaj to take over and tell us about India's planetary science ambitions. Anil.
Thank you. There is ओके ग्रेट, थैंक यू। सो थैंक यू दिवेंदु, एंड आप सभी को नमस्कार। और मैं आपको मून की यात्रा पे लेके जाऊंगा, बट मून के साथ साथ मैं आपको अन्य ग्रहों का जो अन्वेषण किया है भारत ने उसके बारे में भी बताऊंगा। और आप देख सकते हैं कि मैं थोड़ा सा लाइट्स की और कम कर सकते हैं क्या ऑडियो, क्योंकि ये स्क्रीन में कुछ ब्लैक्स और कुछ मूवीज़ आएंगे, कम करना है, बढ़ाना नहीं है। ओके। और आप देख रहे हो कि मैं फिजिकल रिसर्च लेबोरेटरी से हूँ, जो इसको शॉर्ट में पीआरएल बोलते हैं। और ये जो है बहुत ही पुरानी लेबोरेटरी है, डॉक्टर विक्रम साराभाई द्वारा इस्टेब्लिश की गई थी 1947 में, जब हम आज़ाद हुए थे, 11 नवंबर 1947। तो जो भी एक्टिविटीज़ हमारी अंतरिक्ष क्षेत्र में हुई हैं, स्पेस साइंस या स्पेस रिसर्च में हुई हैं, वो सब डॉक्टर विक्रम साराभाई के निर्देशन में हुई हैं। और आप यहाँ पे देख रहे होंगे कि अब्दुल कलाम जी हैं, माधव नायर जी जो बाद में इसरो के चेयरमैन बने, अन्य लोग, ये चाहे आप रॉकेटरी की बात करें, चाहे सैटेलाइट्स की बात करें, चाहे बैलूनिंग की बात करें, सब प्रोग्राम जो है वो डॉक्टर साराभाई के द्वारा पीआरएल में स्टार्ट हुआ। और इसीलिए पीआरएल को क्रेडल स्पेस रिसर्च बोला जाता है। यानी कि आप कह भी सकते हैं कि इसरो की स्थापना जो कि 1969 में हुई, 15 अगस्त 1969 में, 22 साल बाद जब पीआरएल एस्टैब्लिश हुआ, तो पीआरएल इज एक्चुअली द मदर ऑफ इसरो। Now, starting with the program which I'm going to talk about, I will just give you a little bit glimpse about the solar system before going to moon. And we now call it as a new solar system because we don't have Pluto under the category of common planets, 9 planets. It is under the category of dwarf planets. So we have 4 classical planets: Mercury, Venus, Earth, Mars, and Jupiter. Mercury, Venus, Earth, and Mars. And then Jupiter, Saturn, Uranus, and Neptune. These are the 4 big outer planets. If you look at this, you will find that there are 2 classes. One is the inner planets, which is much smaller. Another one is the bigger planets, which is in the outer part of the solar system. Earth, Venus looks alike. Mars is roughly half, Mercury 1/3. Compare them with Jupiter, Saturn, Earth comes at number 5. But Dipankar was talking about the sun. So if you compare this with respect to sun, where is Earth? Earth is a small dot. And on that dot, you can see where is India, where is Ujjain, and where is this place, and then yourself. So we are really minuscule compared to the size of the sun itself. And if you look at the sunspots, which Dipankar was pointing out, the flares which happens from the sunspots, Earth size, the sunspots and the processes on the sun is much bigger compared to that of the size of the Earth itself. Even if you look at the satellites of our solar system, Ganymede is bigger than Mercury, or Titan. Both are bigger than Mercury. And moon comes at number 5 in the number or the size of the natural moons of our solar system. Now let me talk a little bit about the moon and how India has gone into exploring the moon. We started in 2008 with Chandrayaan-1. About a decade later, we came to Chandrayaan-2, and then, of course, the Chandrayaan-3, which is the most celebrated mission of the country. If you look at the Chandrayaan-1, this was a truly international character with 10 different countries participating, 3 instruments going for the first time for exploration of the moon. And this whole satellite, if you looks to be pretty busy because all these experiments are meant to do science. But it also had a gray box sitting over here, which is called MIP, Moon Impact Probe, which was released from the mother spacecraft to land onto the lunar surface on 14th of November 2008, putting Indian flag in the southern pole of the moon. So India has already put Indian flag in the southern pole of the moon. There's a lot of science which has come out. More than 250 scientific publications has come out from that. But the most important is discovery of water. Now we know water exists on the moon, water exists on the surface, beneath the surface, and above the surface. We also know how moon got formed, mini magnetosphere discoveries, and new minerals which are detected. I'll not go into details of each of this, but there are many scientific publications which came out, which I just mentioned, and some of them actually made the cover pages of various journals. How the surface of the moon looks like, let me see if it works. So this is how the surface of the moon actually looks like from the Chandrayaan-1. This is the image from the TMC stitched together to make a movie. And all these spots which you are seeing are craters. Craters right from centimeter to meter to kilometer to 100 to thousands of kilometers. तो मून पे बहुत धब्बे हैं, और इसीलिए कहते हैं कि किसी भी चंद्रमुखी का फेस जो है आप मून के फेस से कंपेयर मत करिएगा, क्योंकि यहाँ पे बहुत सारे धब्बे हैं. Now talking about MOM, that is Indian Mars Orbiter Mission, which is also a very, very important mission. We undertook this mission on 5th of November 2013. using the capability of the PSLV XL itself. And after more than 10 months of travel, we reached the Mars on 24th of September 2014, making India the only country in the world to have the successful insertion of an orbiter around the Mars in the first attempt. भारत दुनिया का पहला ऐसा देश बना जिसने ऑर्बिटर स्टैब्लिश किया मार्स के अराउंड. इसका कार्यकाल था 6 महीने का, बट इसने 8 साल से ज़्यादा कार्य किया. It has 5 experiments on board, which you see over here, and I was directly involved in the Menka instrument when I was working at Vikram Sarabhai Space Center. I will skip this. Now, what it has given a lot of science, but the most important is the full disk images. This is the North Pole of the Mars. This is the South Pole. Mars is also tilted like Earth, 23.5 degrees. Mars tilt is about 25 degrees. So it has seasons, but seasons are very dramatic because as it goes around the sun, its orbit is much more elliptical than that of the Earth. Here you see, it is all frozen. So we came to know a lot of information about the Mars using these instruments. And we also know Phobos and Deimos, which are the 2 small satellites of Mars, including the Valles of Marianas, which is a canyon. The biggest canyon in the solar system is on Mars and looks to be covered with dust and cloud, but sometimes you can see it completely cleaned. So that means this is all because of the seasons on Mars. We also come to know about various valleys like Mangala Valley over here, which can be produced only when there's a flow of fluid on the Mars in the past. Or this big kind of craters, which is one of the oldest craters. It is about 2.6 billion year old craters formed on the Mars. And of course, we also came to know about the exosphere per atmosphere of the Mars, telling that the CO2 dominated atmosphere of the Mars converted to an oxygen dominated atmosphere once you go somewhere around 250 to 260 kilometers above the surface of the Mars. Also, we knew that there's a large loss of atmosphere of Mars happening because Mars has hot argon or you can superthermal argons, and once they are hot means they are more energetic, they can easily escape. So now this data coming from the Mars orbiter mission is rewriting the history about how the Mars has lost its atmosphere. Let me go to Chandrayaan 2 mission, which is much more complex and complicated because in addition to orbiter like Chandrayaan 1, it also had a Vikram lander, and inside the Vikram lander was a Pragyan rover. We all know what happened when we did the landing on 7th of September 2019. We could not land properly. We lost the signal almost like just a kilometer above the lunar surface. But the orbiter with its 8 experiments seen over here are still working for last 6.5 years. Still working. And one of them is OHRC, Optical High Resolution Imager, which is giving you resolution of about 1 feet from 100 kilometers. And this is the one which was used to decide the landing site of the Chandrayaan 3 mission. We have dual frequency SAR, which provides information almost a few meters deep inside the lunar surface. And these are some of the very basic and very important science results which has come out from Chandrayaan 2. Much more are coming because the mission is still active. And the XSM, which actually measures the solar X-rays coming and falling onto lunar surface because moon doesn't have an atmosphere, and therefore all radiations and particles comes and hits the lunar surface. And here you see how the solar X-rays are varying as a function of activity, which Dipankar was telling about. That sun has an 11-year solar cycle. And we could actually trace how the sun is behaving now. But this is actually used to look at the data which is coming from class instrument, which provides you information about the elemental composition. Let me go into further to tell you that, about the Chandrayaan 3 mission. I hope I have still 12 minutes left. Deepan?
You have around
I know.
8 minutes.
8 minutes? Okay, fine. I will start going still faster. So we have this Chandrayaan 3, which is of course the most celebrated one. Since we had the orbiter, we said we don't need an orbiter now. So that's why we had a propulsion module. That is a module which will carry the lander on the surface of the moon. And inside the lander was the Pragyan rover. This is how the propulsion module and the Chandrayaan 3 lander sitting in the mission control in Bangalore. And this is in launch pad. You will see here the experiments which are there on the lander and the rover. We have 3 experiments on the lander and 2 of them on the Pragyan rover. Both of these provides the elemental composition. APXS was developed in PRL. We also have an instrument called ILSA, which is giving you seismicity. Shaste, which is more or less like a thermometer going 10 centimeters inside the lunar surface to provide you temperature distribution. And then Langmuir probe, which provided us information about the plasma density distribution 2 meters above the surface. This is how it looks like in. थोड़ा सा और लाइट कम कर देंगे प्लीज. You will see it much better over here. So this is the Chandrayaan 3 rocket, which is called LVM-3, GSLV Mark 3 in the Sriharikota. That is the launch pad of India. And we had a fantastic launch in the middle of the day. Let me show you if it works over here, the launch.
8, 7, 6,
So this is hardly 30 seconds of the movie.
3, 2,
LVM-3, which is called as the Bahubali, which is the highest or heaviest lift-off vehicle of India. We had the fantastic
plus
lift-off.
5 seconds.
You can see over here.
Here we have a majestic liftoff of LVM-3
tracking.
M4 rocket carrying India's prestigious Chandrayaan 3
थोड़ा सा और
spacecraft.
लाइट ऑफ कर दो फ्रंट का.
प्रज्वलन और सफलतापूर्ण उत्थापन LVM-3 M4 रॉकेट का.
And Chandrayaan 3 was sitting inside in the heat shield over here.
यह भीमकाय रॉकेट आसमान को चीरते हुए अपनी भयानक दहाड़ से चारों ओर कंपन उत्पन्न
ये
कर
वाली
रहा
लाइट
है.
ऑफ करनी है.
जिसे हम
पीछे की
यहाँ
जलती
महसूस
रहे,
कर
इधर वाली,
सकते
फ्रंट
हैं.
वाली.
और यही दहाड़ है जो वैज्ञानिकों को रोमांचित करती है.
So we are all sitting almost like 5 kilometers away from this launch pad,
LVM-3 के उत्थापन
but
के
still we are
साथ
seeing the
हमारे
vibrations
विज्ञान
felt
चंद्रयान
as
3
the
की
launch
चंद्रमा
took
की यात्रा
place.
प्रारंभ हो चुकी है.
After the launch, we went into orbit around Earth, then got inserted into orbit around the moon, and then went into 100 kilometers circular, then went to 100 by 30, and then only started landing. So landing took place on 23rd of August, 2023. I hope many of you must be remembering where we were on that day. I will try to show you little bit glimpses of that. You can see me over here. This is then Dr. Somnath, the current chairman, the former chairman, and all the senior colleagues were sitting in the mission control.
The sensors that are
So this is
updating
the
at
very
this
last
point
leg
are
of
providing
hardly 30 to 40
confirmation
seconds.
of the safety of the landing site.
And we were getting a lot of data to understand what is happening as the Chandrayaan 3 lander was landing. It all starts like this as it lands, and then slowly it becomes vertical as it comes down. Then it does hovering to understand where it is to land, because it is totally autonomous landing. We are talking about AI and ML. We are doing AI ML in this because it is
Currently,
completely
only
autonomous,
2
no command control
engines
given from the
are
mission
now
control.
being fired, and we are nearly
Prime Minister
at
Modi ji was there in South
velocity,
Africa watching it
vertical
live,
and
so you can see him
horizontal.
also on the
We
screen.
were hovering and
2
now we
engines
are
were firing in the last,
approaching the moon's surface.
and then now it is almost like 60 meters. From 30 kilometers, we are just almost landing. And you can see these images, which was also coming us live in addition to many of the housekeeping parameters, the velocities, the vertical, horizontal,
the
the
Honorable
acceleration,
Prime
everything
Minister,
coming live on the
Shri
monitors, and
Narendra
we are
Modi
seeing that everything is
who
working very
is
well.
here to encourage us.
Very soon you will
And
see the
he
loud
is
sound,
critically looking
which will
at
tell
the
us
visuals.
that the lander has really landed. Almost you will see the shut off of this engines. Engines are firing still.
जी हाँ,
Yes, it
आप
is cut
अपनी
off.
स्क्रीन पे देख सकते हैं कि हम लैंडर मॉड्यूल
And this made India the first country in the world to have the landing near the south pole of the moon.
Here from the Secretary Department of Space and Chairman ISRO, Shri S. Somnath.
He is coming.
लैंडर मॉड्यूल पूरी तरह से
फिर से चला दें?
safely और softly
उनको बोलिए जल्दी से आ
चंद्रमा की सतह पे
जाएं।
लैंड हो चुका है। ये हम लोगों के लिए बहुत
So
ही
this was a
गर्व की
very
बात है।
interesting
हिंदी
moment,
में एक
but
कहावत
also a
है
moment of
कि चंदा मामा दूर
pride
के,
for the country.
लेकिन अब हम ये कह सकते हैं
माननीय मुख्यमंत्री जी
चंदा
सही
मामा
समय पे आए हैं।
अपने घर के।
ये डिमांड थी कि मुख्यमंत्री जी को भी ये क्लिप दिखाई जाए। मुख्यमंत्री जी ने देखी जरूर होगी, बट ये एक भारतवर्ष के लिए प्राइड का मोमेंट था जब ये चंद्रयान 3 का लैंडिंग हुआ। ये 1 मिनट का क्लिप है। इसको थोड़ा लाइट ऑफ कर दें, कंप्लीटली लाइट्स ऑफ कर दें प्लीज। इधर की भी लाइट्स ऑफ कर सकते हैं। मुख्यमंत्री जी को जो बहुत अच्छा दिखाई देगा। ये अभी हम 75 मीटर हाइट पे हैं। हम 30 किलोमीटर से स्टार्ट किया था। इट्स ए कम्प्लीटली ऑटोनोमस लैंडिंग, नो कमांड कंट्रोल गिवन। तो आप लोग अब AI/ML की बात करते हैं, ये AI/ML का कमाल है जो हमने चंद्रयान 3 लैंडिंग में यूज किया है। ये 2 इंजन्स इस समय लास्ट में चल रहे हैं। प्राइम मिनिस्टर वाज देयर इन साउथ अफ्रीका दैट डे, सो ही वाज वाचिंग अस लाइव। तो ये मिशन जो होता है सर, वो इस तरीके से 30 डिग्री पे छोड़ा जाता है। उसके बाद धीमे धीमे आते आते चंद्रमा की सतह पे वर्टिकल होता है। उसके
और
बाद ये
हम
देखता है
अब
कि
लगभग
कौन सी
50
अच्छी जगह है जहां पर लैंडिंग करनी है.
कम
इट इज
आ
कॉल्ड
चुके हैं।
ऑटोनोमस लैंडिंग. The mission decides itself the landing site, though the strip is decided.
can
It is
see
something
the
like,
one
aircraft
Prime
landing, strip
Minister,
is decided,
Shri
but
Narendra
where the aircraft
Modi
will touch
who
is known to the
here
spacecraft
to
itself.
encourage us, and he is critically
Very
looking
you'll
at
soon
the
this
visuals.
engines will cut off and the landing will happen.
जी हाँ
Yes, this is
आप
cut
अपनी
off.
स्क्रीन पे देख सकते
Landing हो
हैं
गया.
कि हम
And you can see the
अब
responses
लैंडर मॉड्यूल
from the public. All mission control was very happy because we have
People
achieved the
are
feat,
applauding.
making India the
Let us
first
all
country
wait to hear from
to
the
land
Secretary
in the
Department
southern
of
polar
Space
region.
and Chairman ISRO, Shri S. Somnath.
Prime Minister was also very jubilant,
लैंडर मॉड्यूल
waving
पूरी
the
तरह
flag.
से सेफली और
इसके बाद दुनिया किस प्रकार से रिस्पॉन्स कर रही है?
India has done it. It has become now the fourth country to land a spacecraft on the moon after the US and China and the former Soviet Union. Just moments ago, we're talking just a
India has made space history, becoming the first nation to soft land a spacecraft on the moon's south pole.
India has become the first nation to successfully land a spacecraft near the south pole of the moon. The country's PM Narendra Modi has praised the achievement, saying that the mission's success belongs to all of humanity.
The spacecraft Chandrayaan-3 is attempting to become the first to land on the moon's south pole.
India is the first country in the world to land a spacecraft near the moon's south pole, a moment of history for the country. It was a tense final 6 minutes as it descended onto the lunar surface. Let's show you the moment. First of all, let's take
Space Agency is celebrating the successful moon landing of its Chandrayaan-3 spacecraft.
Okay, now India's lunar probe Chandrayaan-3 has landed on the moon's south pole. India is the first country to touch down on this part of the moon, which is believed to hold pockets.
We begin with some historic news. India has become the first country in the world to successfully land a craft near the moon's south pole. Prime Minister Narendra Modi was watching the mission from South Africa and congratulated the team back home.
So this is how the whole country, not only country but the whole world was celebrating because India became the first country to land near the south pole of the moon. But we in the mission control were busy how to take out rover because we had to do science and rover has to come out and move on the lunar surface to do science. I will show you one of the clippings how the Pragyan rover started moving onto lunar surface to save time. So you will see this is the Pragyan rover after getting charged, released, it started moving. You will see the shadow. You will see the Indian flag and emblem here. And this is the first touchdown of the rover. And it started rolling. And this was happening in front of our eyes in the mission control, and we are really, really happy in terms of seeing our baby making the first step. After that, you'll see the tracks of this Pragyan 3 making as we move on to the lunar surface. And then this is the image of the Vikram lander taken by the Pragyan rover. So, बड़े भाई का विक्रम का छोटे भाई प्रज्ञान ने photograph लिया. And this landing site we all know, now it is called Shiv Shakti, and we also celebrate 23rd August as the National Space Day. जो लैंडिंग हुआ हमारा शिव शक्ति पॉइंट पे, उससे प्रज्ञान रोवर ने इधर गया, यहाँ पे एक बहुत बड़ा क्रेटर दिखाई दिया. We went back, we started moving this direction, but then the geoscientists and lunar scientists in the mission control said, this is a fresh crater, we should go in this direction. We navigate through this, went into this direction. This whole distance is about 103.5 meters, covered over a period of 10 days. A lot of good science has come out. More than 50 scientific publications in high-impact journals has come out, including talking about how the temperature distribution takes place in the top 10 centimeter. Now we know that temperature difference between the top layer and 10 centimeter down is more than 50 Kelvin. 50 Kelvin. You can imagine 10 centimeter इतना होता है. इसके अंदर 50 डिग्री सेंटीग्रेड केल्विन का टेम्परेचर डिफरेंस पाया गया है. We also came to know about the seismic activity. Whenever rover movement was there, we captured it. We know from Rambha LP observations that the plasma densities is or the order of few hundred particles per cc, which is also very new information, the first in the time. And using APX as instrument, which was developed in PRL, we came to know about the various elements which is present on lunar surface, including sodium, magnesium, aluminum, silicon, calcium, potassium, titan, manganese, and things like that. But we also found little bit higher magnesium, which suggests that there has to be material which has come out from somewhere at this landing site. And then we propose that it has come out from the South Pole Earthquake Basin. And because of this new conjecture, it came in the Nature paper. But then we corroborated this with more observations of volatile, and we found higher abundance of sulfur and lower abundance of sodium and potassium, which in turn suggests that yes, the hypothesis which we gave in the Nature paper is correct. What next? What next? India is now talking about the lunar sample return mission in Chandrayaan 4 mission, which is going to be much more complex and complicated than Chandrayaan 1, 2, and 3, because we not only had to land, but we had to push back the sample in the orbit around the moon. From the moon's orbit, it has come to Earth's orbit and then land onto the Earth's surface. So there will be a lot of dockings, and that's why we are doing docking experiments. Last year beginning, we had done space docking by combining two spacecraft, joining together and taking them out in Earth's orbit when they were moving at a speed of about 26,000 kilometers per hour. So this is going to be a very complex mission. In addition to this, we are talking about Chandrayaan 5, which is going into the polar regions, which is called LUPEX. It is a ISRO-JAXA mission or India-Japan collaboration. But we are going right at the southern polar regions and then landing at this site, going into permanently shadowed regions. That means they never see the sunlight. See what is present there. So rover is there and lander is there. Lander is coming from India. Rover and the launcher will be coming from the Japan. This is also a very complex mission because you have to land at a location where you will have sunlight continuously for 6 months. Batteries will be charging both the rover and the lander over here. Rover will go inside and come out, go into next one and come out. So it is a lifetime of 3 months. But we expect that it may last still longer than that. And this one is the one which will give you first information what is present in the deep freezes, which you call as permanently shadowed regions. We are also talking about Venus Orbiter mission, which is a first Indian mission to Venus, where we are trying to orbit around the moon, but now we are also planning to have a probe which will go through the atmosphere of the moon, to the Venus, and probe its atmosphere. And this is going to be a very important mission from the country because for the first time we are going to explore the Venus. Venus has not been explored much by any other country other than a couple of missions which has gone like Magellan, Venus Express, and things like that. We are also talking about Mars lander mission because Mars orbiter we have already done in 2013 itself or 2014 and lasted for 8 years. Now we want to land straight away onto the moon surface, Mars surface, and then move like what we have done using the Pragyan rover on the moon. And this is also going to be a very important mission because it is for the first time that India will be landing on a planet which has an atmosphere. This is the future track. If Deepu allows us to talk a 1 minute, over time I know, but 1 minute to tell you what is next. We are talking about Chandrayaan 6, Chandrayaan 7, Chandrayaan 8, and then crewed mission. Finally, Indian Gaganyatri landing onto the moon by 2040. So this is the mission of the country. Pradhan Mantri ji has already given us this mission that Indian astronauts should land onto the lunar surface by 2040. And ISRO is continuously working on this. And that's why you're seeing there has to be a series of missions before even human landing takes place on the moon. Once we have done that, we are talking about settlement on the moon. We are not talking about just exploring the moon because we have to see whether we can use moon as a base for future explorations. And therefore, we are talking about the Bharatiya Chandra Nivas. That means human settlement or Indian settlement or Indian colony over the lunar surface. So this is a very long-term visions which is achievable in the next 2 decades or 3 decades or so. But we have to start working from now. If we talk about Chandrayaan 1 in 2008, the work started in 96, 97 itself. It takes 10 to 15 years to actually realize this kind of complex missions. So the future is all very bright for youngsters who are sitting there. And all the data which comes from this kind of missions is available to public, to scientists within the country and outside the country to do the exploration. Thank you so much.
On behalf of the audience and the esteemed guests here, I would like to thank Professor Anil Bharadwaj for talking to us about the exciting missions that ISRO has achieved until recently, and also wish good luck to ISRO for the future Chandrayaan, Venus, and Mars missions. ISRO is making us very proud, and we are always with you. Thank you.
Thank you.
Thank you. On behalf of the scientific community of the nation, राष्ट्र का वैज्ञानिक और एस्ट्रोनॉमर्स का ओर से मैं चीफ मिनिस्टर डॉक्टर मोहन यादव को स्वागत देता हूं हमारे बीच में। नहीं, मैं एक्चुअली इस ऑब्जर्वेटरी के बारे में पढ़ रहा था और मेरे को ये पता चला कि आप जब एमएलए थे तब से ही इस ऑब्जर्वेटरी को प्लानिंग आपने सपोर्ट किया है, प्लानिंग किया है। दिस इज़ वंडरफुल। I mean, even before he was the chief minister, he has been working for astronomy in this part of the country, and I hope that the astronomy and scientific community of the nation will get behind Madhya Pradesh and Ujjain when they host the Mahakumbh and showcase Ujjain as the center of astronomy in the country. So welcome again. Moving forward, we have been talking about space. स्पेस और हमारे एक आबहवा के बीच में जो लेयर है आयोनोस्फीयर, अपर एटमॉस्फेयर, वो स्पेस का जो इन्फ्लुएंस होता है हमारी पृथ्वी के ऊपर, उसको इन्फ्लुएंस करता है। उस लेयर के ऊपर काम करना भी वेरी इंपॉर्टेंट है स्पेस साइंस के लिए। उसका एक एक्सपर्ट हमारे बीच में है, डॉक्टर तरुण पंत। ही इज़ द डायरेक्टर ऑफ स्पेस फिजिक्स लैबोरेटरी ऑफ विक्रम साराभाई स्पेस सेंटर फ्रॉम तिरुवनंतपुरम। I welcome him to the stage now to speak about our favorite planet, Earth. पृथ्वी के बारे में बात करने के लिए, हमारे आबहवा, हमारे क्लाइमेट स्पेस से कैसे इन्फ्लुएंस्ड होते हैं, उसके बारे में बात करने के लिए। सर तरुण, प्लीज टेक ओवर।
Thank you, Dipu. So I thought, I'll bring you a little closer to Earth. We started with the sun, and then we talked about the mission, ISRO's mission. And now I thought I'll bring you closer, as Deepu said, to Earth's upper atmosphere, and what is happening in the near Earth environment. So I thought the topic that would be very relevant for that is the research, what is happening today, the sustainability of this region, whether we can carry out, continue in terms of the sustainability, we can talk about it, and what are the challenges that we face. So I hope that by the end of this talk, I'll be able to give you an impression what is happening in this particular area. Globally, when you talk about a nation, how it is faring in the international arena, the one metric that is used is the consumption of power, right? The per capita consumption power of that nation. And if you look at India in recent years, even though India comes at a 12th or 13th position in the globe, but then the growth in the power consumption in India in recent years had been more than about 52%. And that sort of tells us that what sort of energy requirements we have on the ground. That is the need for the... Okay, all right, sir. Yes. Yeah. Okay, so this is to give you an impression that what kind of growth we are seeing in India in our developmental structure in terms of the metrics that we use in the international arena. And this is very, very important. Why it is important? Because this is directly related to the growth of science in India. Not only that we need more and more space-based infrastructure in India, our aspiration as a nation is growing. As our aspirations are growing, we are also growing our ambition of having more bigger space programs, as it was as it was made clear by my previous speakers. We need more space-based measurements. That is very, very clear. But then today, if you look at the in terms of the infrastructure that India has, we kind of address all the sustainability goals that the international arena is currently having. We are addressing all these goals. Not only that, as I said, our aspiration for having more and more satellites are growing. Our number of satellites in space are increasing. So the point is, as our infrastructure in space is increasing, okay, it is also leading to a factor which we should consider here, and that particular factor is, oops. Yeah, that's okay. That's okay. So, yeah. So this requires, as our space infrastructure is increasing, as I said, it requires a special kind of understanding of the near Earth space, where all these space infrastructure is sitting. And that particular awareness about that is known as the space awareness. Actually, this is a term that you would be listening very frequently. We as a nation, we should be more space aware. Okay, and why we should be more space aware? It has actually two aspects. It requires this space awareness is needed from 2 points of view. One is that the science demands it. I will tell you why the science demands it or how it is. And second is the technology. Technology also demands that we should know what is happening in our near Earth space. So the very first point, from the technology point of view, as you know, our space, if you look at the space, the satellite programs initiated by the launch of Sputnik in 1957, right? So that was the very first satellite which was launched in 1957. But today, if you look at the number of satellites, the number has grown. Actually, every dot in this point on the right panel is actually a satellite. Okay, so this is to highlight, to tell you that, this is the situation in our near Earth space. The space around Earth is actually now cluttered with the satellites that Professor Saraswat was mentioning in his lecture before noon. And this is becoming more and more. Actually, the satellites, the number of satellites in some of the programs, international programs we are talking about, is getting into thousands, right? So this is going to be even more cluttered. So anything that we need to do in this region, we need to understand how to remove this clutter. And this is going to be a major, major challenge. And I must tell you that most of these satellites which are near Earth are in the altitude regions which are of concern, which are needed for Earth's observations, like the altitude from, say, about 200 kilometers all the way up to thousands of kilometers. So this is very, very important. This is also important that when we have our missions, when ISRO is conducting as a nation, when we are conducting our experiments in space, when our astronaut is doing the spacewalk, there is nothing that harms it. And actually, some of these space debris, these objects which are in the near Earth space, they can actually harm the satellite or the infrastructure that we have in space. So we need to be really very careful about this, and we should have a correct idea of where it is, whether it is going to be detrimental to our system, and that understanding of space awareness is very important. There is another aspect which is dealing with the science, as I said, right? So in this altitude where these satellites are, there is another important point which Dibindu was mentioning in the beginning, which Dipankar was mentioning, is the atmospheric drag. Actually, the altitude where the satellite is traveling or going around the Earth, right, it also experiences a kind of drag. So every satellite with it carries a certain amount of fuel, right? So what happens is, as the satellite goes around the Earth, makes the measurement, it loses the orbit, right? But then since it has fuel in it, it is corrected, it is lifted, and it is pushed back to that orbit. But you imagine that now once the satellite becomes defunct, or if the amount of the fuel is not enough, or there is one more factor, which is the atmospheric density at that particular altitude. If it is not properly understood or known how it is varying, then what would happen is our calculations would be wrong, and we'll put a satellite there with a wrong amount of fuel in it. And when it is needed at the correct time and space, when we need the satellite to make a measurement at that given altitude, it won't be doing it. We will not be able to push it to that right altitude. And what happens is, as you can see, any defunct object in the space, it actually falls. If it is not corrected, it falls very quickly to the lower altitudes. And you can see that this is the defunct Tiangong space shuttle of China. When it became defunct, within 1 year, you can see that it came down from 350 kilometer altitude down to about 100 kilometer. And beyond that, once it enters into that region, because of the enhanced density, it burns, right? So this is a very, very important point. Means we need to know the density of that altitude where the satellite is going to be placed, and how it is going to vary with the energy input from the sun. Actually, Earth's atmosphere is directly coupled with what is happening on the sun. So if the sun is active or the energy input from the sun is high in different spectral regimes, what we see is the atmospheric density in the region where the satellites are sitting is also going to change. And if it is going to change, then it is going to affect it is going to increase the atmospheric drag. And we should be knowing about it correctly. So our science also demands that we should have a correct understanding, or correct space situational awareness. And that is why we should know what is happening on the sun. When it comes to further down, this satellite altitudes are also the altitudes where, because of the energy input from the sun, our neutral species get converted into, or gets ionized and produce the ionosphere. And the ionosphere is used for the ionospheric communication, our trans-ionospheric communication from the satellite to ground. This plasma, the presence of plasma, ionospheric plasma, is very, very important. Okay, but then this ionosphere plays a very, very important role in one other way. And that is, as you know, any radio wave which is traveling through a plasma medium, because of the change in the refractive index, it undergoes a refraction. Okay, so you can see that because of the refraction, the range that we talk about, the range that we receive on the ground, can have a major contribution of change happening due to the presence of ionosphere. And a certain amount of change can happen due to the presence of water vapor in the lower atmosphere, right? So these two combinations put together will decide how you are receiving a signal from a satellite. Let's say your GPS signal. GPS signals, whenever we have ionospheric irregularities or the changes, the major changes in the ionosphere, we see that they cause errors, the range errors, the timing errors in the GPS system also. In every frequency, because ionosphere is actually frequency dependent. So if you use one frequency, it will have a certain contribution. If you you change the frequency, the contribution will change, but nonetheless, it will be there. Okay, so it is very, very important to know what is happening in the ionosphere. The ionospheric density variation is very important for the satellite-based or any communication that we are using through the ionosphere. In fact, if you talk about the delays, earlier the general understanding is that when the sun is active, when the sun is influencing, the major influence of that is happening at the polar latitudes, because at the poles we have because of the auroral activity, the major changes are happening there. But of late, there is a realization now that even the countries like equatorial nations like India are also vulnerable to the induction-induced currents on the power systems, on the gridding, on the ground, and also in terms of the range delays that we use in the navigation. So our navigation, if you see, this is a model which shows that the error is maximum across the globe. If you see, the maximum amount of your delays occur near the equatorial countries, right? Where the number zero you are seeing. Around that region, we see the maximum amount of range delay. So what it shows is that we also need to worry about what is happening in this ionosphere because of the changes in the sun. So sun influencing our upper atmosphere, producing changes, and because of that, changes happening in the range, in the navigation, and all other density in the upper atmosphere, and affecting the space infrastructure, because these factors ultimately boil down to our structures which are placed there. I'll skip this. There is one important factor which Dipankar was mentioning. When the sun becomes active, right? It is something like, it is like a storm which is happening on the sun. Okay, there is an equivalence. If you talk about the cyclone on the Earth, right? The cyclone is a process where water is actually the agent which couples the processes, right? Similarly, when a storm happens in the sun, the magnetic field is the property which connects what is happening in the sun with something happening on the Earth. So sun and Earth gets coupled through this magnetic field, which is present both in case of Earth as well as in case of sun. And we really need to know this, because I'll tell you, this is what Dipankar was showing. Sometimes it can be really, these structures on the sun can be really eruptive. So they can carry with them a lot of magnetic field, energy, and mass, right? So this comes into the atmosphere and blow towards the planets, including Earth, right? And when it comes to Earth, what happens is our Earth's magnetic field. We all know that Earth has a dipole magnetic field, right? So which sort of protects it all the time. But then what happens is when the sun becomes active, you are seeing on the right side, on one side from where the solar particles are coming and hitting. Yeah, 3 minutes. Sure. When the solar particles are coming and hitting, that side the magnetosphere gets compressed, and the magnetic field of the sun, which is coming from the sun, gets connected with the Earth's magnetic field, and the energy travels through that into Earth's atmosphere, and that is exactly what is shown in this figure here. And this is ultimately, you will see that it comes down to the polar latitudes and then shows up there. There is one more factor which we need to bother about, and that is, you imagine that, so on the left side you are seeing the satellite based observations of the sky. If you look at Earth from you go out of the Earth and then see from there. So what you will see is the central globe, and around that Earth you will see a globe, which is actually a resonant scattering of particles. So you will see an emission which is around that. It's basically coming from the plasma sphere. Okay. So what happens is, when the sun becomes active, or when there is a geomagnetic storm, it's very, very interesting. You see on the left side, top left, you see the extent of that globe is almost about 4 Earth radii from the surface, right? But then if you see the number 2, the second one, when the storm hits Earth, right, the whole thing gets compressed. And the compression, you can see that it comes down to about 2 solar Earth radii. So it means it gets compressed more than 2 Earth radii. And now you imagine, you come to the right side of the image. If you have a satellite, which is sitting on the side from where the solar particles are coming and hitting, and if it is getting compressed, what will happen is your satellite gets exposed to, because magnetic field will push beyond, and your satellite is now exposed to what is coming from the sun. And this is extremely detrimental to any satellite, any kind of satellite. The bigger satellite, because geostationary platforms, we usually have satellites which are doing the remote sensing, and these are bigger ones, right? So we need to be extremely careful, space aware, if we want to have to protect our infrastructure in space, right? And that is very, very important, not just from science, but from the point of view of technology also. So what is the state today, right? What is it that we are able to do? So the need is, we need to have a ground-based setup. Of course, satellites are needed. We need measurements in this region. Not to say that we don't need satellites. Satellites are needed very much. But then we need to have a framework of data, models, and then these data giving us information at different time scales. Because the radiation from sun travels in 8 minutes to Earth, okay? But particles take hours to reach, right? So our modeling that we talk about, right, it has to deal with at both scales, okay? And which is a very tricky problem. And that is why I'm showing that, we need to work at different scales, which varies from, minutes to days. And then on the right side, we need to have a infrastructure, the full infrastructure other than satellite in space on the ground. So as Dipankar was saying, that we need to have telescopes. Similarly, we need to have on the ground, we need radars, we need to have magnetometers, we need to have ionosondes, air glow measuring instruments, and a network of radio receivers. So these are the ones which give the information of what is happening in this satellite altitudes, right? So that is the need of the hour. So with this, I'll stop my presentation, and I hope that I have given you a flavor that why this region is important and why we should be having some sort of a space awareness as a nation. Thank you very much.
Thank you to Dr. Tarun Pant of Space Physics Lab for telling us about the ionosphere and taking us back to the sun. Our final speaker of the day has traveled from Japan, Professor Yasuhide Hobara. Professor Hobara is from the University of Electric Communication in Japan, and he heads a couple of different centers. The most relevant for his talk is he heads the Center for Earth Environment Station. So Professor Hobara is going to talk about natural hazards and how do we use space science and space technology to forecast, predict, and assess natural hazards. So this is really coming down to earth and telling us about the usefulness of space science and space-based technologies. So Professor Hobara-san, please go ahead.
Okay, so now they are preparing my slide. Okay, it's coming. So before starting my talk, I'd like to appreciate the local organizing committee of this meeting, and also the Professor Datta from IIT Indore, and also the Dr. Sasmal, now he's a moderator. Okay, so let's start my talk, and just make sure that if this function work. Okay. All right. Okay. Okay. Okay, so so this slide shows the monitoring and predicting terrestrial and the space environment by using radio sensing technique. So I'm a radio scientist working on various different fields, and then as you can see now, space weather things. It's already previous speakers talked about, so I will skip it due to also time constraints. I'm going to focus on the other field, like an atmosphere and the lithosphere, right? And if you look at here, the space weather effect is of course important for the modern technology, satellite communication, and so on. But in the atmosphere, as you know, nowadays we have a lot of natural hazards here. You can look at the heavy rainfall that's making the flood, and also tornadoes like gust wind. This is a very big hazard for the air, air traffic as well, and also the housing sometimes blow away, and also the agriculture. And then, needless to say, in the lithosphere, most the intensive hazards is earthquakes. These two phenomena which is hazard in atmosphere and the lithosphere, we share. Actually, in India and also Japan, we have a similar one of the biggest problems. So how we radio science can tackle these problems for the mitigate the damages and human loss of human lives. That's what I'm going to talk about today. Now, the outline, I focus on two things here today. One is how lightning discharges can contribute to these severe weather phenomena, like making a flood and wind. And also another stuff, the electromagnetic phenomenon with seismic activities. That is another one. Then additionally, I'm just talking about the lightning energy things. The previous speaker talked about how much your country grew up for last 10 years. And 10 years and a 52% increase of electricity. That's a very big increase. So your country is really developing now. And then associated with this kind of increase, stability of power supply is very, very crucial. Yeah, especially, for example, semiconductor industry and whatever. And then your daily life too. This is very important technique. Now we're facing such kind of problem for stability after the nuclear reactor accident, though it's quite important. And then lightning is one of the major hazards for the power grid companies. So I'm talking about that as well. Okay, let's start from the A, the lightning, and then total lightning observation. Sorry, let's go. Okay, just before that, I just to make sure that I got borrowed the slide from my colleagues. And, this is the number of deaths from a natural disaster by time 1900 to the 2025. Yeah, there is a lot of different types of natural hazards, but nowadays you can see mostly the earthquake, sometimes the earthquake and the flooding and the temperature related, so the weather related phenomena. Two phenomena are quite important. And then, sorry. To just make sure. Okay, in the case of India, you see the two major hazards. One, the earthquakes. This is the Gujarat earthquake, and this is the earthquake in Indonesia, but you have got suffer from tsunami. And then recently, the blue ones, these are flood. That's definitely this is a meteorological hazard and associated with a lot of lightning as well. So this is the space that we are working on. Now, there you go. Heavy rain and tornadoes. So quite recently, 2021, you remember probably the European flood in July, and also in Japan in 2020 is a big flood in Kumamoto. And not only that, quite recently also we have the flood in almost every year almost everywhere in my country now. So this is very, very serious. Then what we do, sorry, this is very difficult to. Yeah, to tackle this problem, to mitigate, the forecasting is quite important. However, the major problem is that this kind of flood is caused by sudden development of the thunderstorm cloud. It is quite difficult to detect precisely in time because in space. Because, sorry, but I'm not familiar with this. Okay, how we are moving. Yeah, okay. Now, the thunderstorm clouds, which causing such kind of heavy precipitation, develop so quickly, typically less than 10 minutes. In a high-speed radar, presently operating even in Japan, high-speed radar say, one shot in 3D, then 5 minutes. It takes 5 minutes. It's not enough. So we need some more high temporal and spatial resolution technique to detect such kind of phenomena be going on. Then now we focusing on the lightning. Especially we define so-called total lightning. Normally we see the lightning in channel from the cloud to ground, but this is not enough. We try to look at the in-cloud lightning, which is normally difficult to detect from ground-based systems. So we have hopefully a special types of lightning detection network nowadays in Japan. So we observe nationwide with total lightning. Okay. So this is our network, in a ground-based network of total lightning, consisting of nowadays in 17 sensors nationwide. And then we continuously measure it round the clock. Then first results regarding the tornado, the gust wind, which occurred in Japan. If you look at the temporal dependence of the lightning numbers here in the time, and this is a number of the frequency of the total lightning, which is showing the blue. This is the summation of the in-cloud lightning cloud to ground. As you can see, the dramatic increase in 20 minutes before the touchdown of the tornado. Well, I don't know that if the tornado occurs in India, but seems to be a gust wind also, like a downburst. This is the precursory phenomena of the lightning. It quite often happens. The another thing, the lightning is very useful to detect the heavy rain. If you look at here, the horizontal axis shows the total lightning flashes, and the vertical axis shows the precipitation volume. Amazingly, you can see a very straight line here. It's a correlation, very strong correlation between the lightning and the water, heavy precipitation. And then different storm as well. So this is a very interesting nature. And this is actually the volume. That if you count the lightning, and then you can estimate how much rain will fall. But another important thing is that the temporal dependence. It's not only the amount of the water, but you need, if you have some precursory phenomena in time, and it's quite important as well. Indeed, total lightning, the lightning number increase 10 minutes before the maximum of the water fall down. So that is why you can this can be total lightning can be used for the short-term warning of the heavy rainfall. And if you live in a rural area, it may not be a very, very effective. But if you live in the city center, nowadays you have a lot of you have metro system and you have underground paths in a city, and then there is not so much a drainage system yet. So in this case, the water is filling very easily. And even we have in Tokyo, we have a problem even nowadays. The weather changes, climate change is so rapid, and we cannot cope with the drainage system yet. So that is why this kind of 10 minutes even warning is quite important to save your life. Just evacuate from the underground facilities and so on. And the car park is also filled by water. It's last year in my country, so it was amazing. Now, carefully moves. Yes, another thing. This is about the consumption of the energy, right? One of the important lightning hazards, not only by hitting by lightning. That is also the big problem in India too. The few hundred people are killed by lightning every year. That is actually a well-known association. But we are now talking about energetic lightning. I'm talking about energetic lightning. The energetic lightning makes the damage of the power grid systems, so that, as you can see, melted down overhead wire or even a burnt wind turbine blade. So on the way from Ajane to here, I saw a lot of wind farms, wind turbines generating. This is a very important, the energy source for nowadays. Instead of the oils and the nuclear power and system. So, but those systems suffer from lightning. This is one of the most serious hazards for these systems. So, not all the lightning gives you such kind of problem. The lightning with large charge moment, especially large charge in Q, is they make such kind of serious damages to the systems. The lightning with large Q is very difficult to detect. Even a power grid company in Japan is struggling to get those. And we have recently developed a system by using the very low frequency wave, especially extremely low frequency wave in the so-called ELF. And then, as you can see, the system is consisting of just simple electric and magnetic receivers. Yeah, I mean, even a few hundred kilometers away from lightning location, because the low frequency wave can propagate a long distance. The previous speaker said that ionosphere is actually, you have almost a conductor here in that frequency, so that they propagate in Earth and the ionosphere for long distance. And we can get, the pulse from lightning receiver, and from here, we are able to get the lightning moment, lightning charge, Q. This is a crucial parameter for such kind of damages. And then when we make a map or distribution map, such kind of energetic lightning, in summertime over Japan, we can mostly concentrate on the land. And these kind of information is very important for the renewal of the power grid system in Japan that actually is used. We are collaborating the collaboration with a power grid company, and then they actually use this map to decide to prioritize renewing the power grid systems. Now, so those two, I talk about two different things now. I mean, the space, the severe weather prediction, and another one is the energy of the lightning. Then these are based upon the ground-based measurement. So it's quite limited, right, in the space, like, about my country. But this is also possible nowadays to detect from the space. The one of the things, the extreme weather prediction from space, that's the geostationary in orbit. So this satellite is called the geostationary lightning mapper. Unfortunately, we don't have it yet. US and European countries and China, they have this kind of geostationary map. And then it has an optical sensor, and then 24 hours, they can monitor the lightning from the space. Yeah, okay, it's not a visible light. It's oxygen line, so that's why day and night they can measure it. It's very, very modern technology. And then the heavy precipitation, tornado, that's I say gust wind I told you. But not only that, hail, hurricane intensification can be detected by lightning. And another application, I don't know exactly, but in case of India, the wildfires are quite rampant nowadays. And for example, US, we got much dry weather. And then especially in the lightning with light charge moment, that's also the hit the trees and then just fire ignited. So this is quite important. And then needless to say, aviation safety, right? Because the lightning is one of the major hazards for the flight. Okay? So this is very important technology in the future also. And then I'll just briefly introduce the Japanese ISGRIMS mission, which I'm involved, and this is the first Nadia mission, the global lightning, and also the sprites. That is actually the fireworks from the lightning in ionospheric altitude. That is the combination of optical and electromagnetic emission there. This is installed in the GEM, so-called in outside ISS here. One of the unit here, right? And they consist of CMOS camera and photometer and.
Operation,
okay.
3 minutes.
Okay, thank you so much. And I'll try to wrap up. And the VLF antenna and so on. Well, so this is the distribution of the lightning map from ISS, and then we can calculate the charge moment change, the energy of the lightning based upon optical measurement. So believe it or not, actually very good correlation we found the first time. So that's why we are getting the electrical energy from the lightning, the map here, and this is coinciding with the sprite measurement, which means that it's proved by that sprite ignited by the high energy lightning is a renowned phenomena. So that is why it's perfectly coincide that our measurement by optical emission is very correct. So we can utilize this method for the lightning energy estimation. Now, the seismic phenomena. I'm just talking about a little bit. Time is limited, so that's why I'm just shortly describe. And now the seismic hazard. Before seismic activity, we have a lot of different types of electromagnetic phenomena we observed. One of them is the ionospheric phenomena perturbations. The another one, the atmospheric perturbation. I'm just talking about ionospheric perturbation, then somewhere around the atmosphere too. Okay, this is one of the results, famous result in after the Tohoku earthquake 2011. That's in the March, March in 11. March 11 in 2011. Yeah. So this is so huge earthquake occurred in overseas here, magnitude 9, and then probably you saw by TV that how the suffered from tsunami and many people died, and then we see the very distinctive ionospheric perturbation by using the VLF network in almost 1 week before the quake. And then not only that one, in the big earthquake, we have a quite similar phenomena observed. Then the updated results. For example, I'm showing here is the magnitude 7.0 of earthquake in Noto Island in January 1st, 2 years ago. January 1st is a celebrated day, but it's very pity that the quiet days of big earthquake occurred in the countryside. Then we have the network here in the VLF network, and then we see the peculiar precursors, like 1 day before the quake. This is the date of a quake on January 1st, and you can see the wavelet spectrogram in this perturbation in the ionosphere showing, and you can see the enhanced area here. This shows some oscillation in the ionosphere in 40 to 260 minimum minutes range. This is so-called internal gravity wave range. So this is a very distinct phenomenon, and then space weather effect is almost none because it's quiet. So it's presumably coming from the down, the lithosphere and the atmosphere, and then coupled to the ionosphere. Now, those are the previous, the results are from, the precursors in like 1 to 7 days. But here, I'm just talking about the imminent earthquake as well. Finally, imminent earthquake. That means even 1 hour before earthquake, if it's warned, what do you do? Yeah, you can evacuate from the building. Yeah. 7 days, 8 days, this is for maybe the mostly the authority, right? But in 1 minute, 1 hour before, within 1 hour before, the loss of life drastically decrease. So we are looking at some signature for the even imminent earthquake. The interesting is that quite recently, the ionospheric tech, so-called used for GPS technique, same as the GPS technique, they have detected the very distinctive anomaly starting from 1 hour the earthquake in different places in the world. Repeated. It's quite reliable. And we also look at the anomaly in the VLF, but the VLF is sometimes yes and no. Then the problem is that even we get such kind of anomaly, we don't have any proof in a ground-based measurement. This is space measurement, right? And then very recently, we get some signature in the atmospheric electric field. So the atmospheric electric field exists always in Earth, around the Earth's surface, but mostly affected by normally lightning, right? But before the earthquake, we found such kind of bulbs, enhancement in the frequency range in the same range as we see in the perturbation of the low ionosphere. And then we look at the many other cases and they found out also some depend by events, but it varies, however, within an hour almost. So this might be the great signature to the coupling signature of the earthquake preparation region to the ionosphere. The firstly proven that by using the atmospheric electric field measurement, which means that atmospheric oscillation measurement field is oscillated by the atmospheric gravity wave, which propagate upward, right? And at that time, space charge density is modified, so that's why we see the modification of the atmospheric electric field. But when we reach the ionosphere, we see the ionospheric anomaly. So this is one of the scenarios what we are thinking about. Now, so I'm sorry the time is over already. So summarizing to conclude, today I delivered the talk regarding the observations of electromagnetic waves at the different frequencies, and the different phenomena, right? In extreme weather and the erratic lightning will be predicted by the radio wave in different frequency range, like DCHF for the DC and HF for the precipitation things, and lightning energy for the ELF range, and the optical. If we have the optical observation from the space, we can do for both. Now, for seismic activity, you can using the LF and the VLF measurement in the ionospheric anomaly and the GPS tech for the imminent precursors together with the atmospheric electric field. So this is very important for the precursor signatures for natural disasters, natural hazards. So these informations now we try to utilize for the disaster risk reduction. Okay. So before my concluding really talk, I'd like to show you one slide that the Indo-Japan collaboration, this is the hazard, space, weather, and the ionosphere. This is just started from November last year. And then a project overview is international collaboration between Japan and India, focusing on advanced electromagnetic observations. So we have a very strong colleagues from different institutions from Kolkata and also Indore IIT and also Kolkata region as well. And then it's an important thing is that that we try to make the model data integration in both countries. They have a common platform, and we analyze jointly the data, big data, and also not only that, we try to make some human resource development in both countries. So I'm very look forward to collaborating with Japan, not only with your country, okay, India. Okay, thank you so much. Sorry for that.
Please stay on the stage. May I request the other panelists of the session to come up on stage, and on behalf of all the participants and the audience, let me thank you. This is a land of great significance where India's traditional pursuit of wisdom for the cosmos and cosmic time meets modern advances in this symposium. And we are very thankful for you for making this trip from all the way from Japan to be part of this journey. Let's give him a big hand. We have all the panelists. Please have a seat. May I now request Dr. Sudipto Shashmal, who is from the Institute of Space, Astronomy and Planetary Sciences at Calcutta, to come up and provide a brief summary of the session, following which we will take some questions, and if you want to have some discussions, we can have that for about 10 minutes. आपका कुछ प्रश्न या जिज्ञासा है तो हम उसके भी थोड़ा समय रखे हैं, 5 से 10 मिनट. एक समरी होगा अभी प्रोग्राम का, उसके बाद आपका जो जिज्ञासा है या प्रश्न है आप कर सकते हैं. Sudipto, can you please come on stage and just start?
Thank you, Professor Nandi, for the introductions, and I would like to thank the present dignitaries, the organizers, our eminent speakers, and the audience and the guests. So let me confess something, that I found this session is extremely well structured, from where we started from the sun, then come out to the interplanetary medium, then talking about the planets and the natural satellites, about moon, and then Earth, planet Earth, its atmosphere, and finally about the mankind or the human beings of the planet, about the hazards. So the entire journey was covered by two major things. First, the excellent legacy of the Indian space program before and after the independence. And the next one is the exceptionally rich resources about the instruments both from ground and space-based systems. So all the speakers have explained in very detail about their feasibility, their achievements, and the glory made by our space program throughout the globe. And one important thing is that as we are talking about the Indian space program, about its future and other things, it is very important to note down that presently we are having some kind of emerging India and also the National Education Policy 2020, where students are being encouraged to come into the space program. So what Professor Hobara just mentioned about the developing of human resources, it is very, very important. And the most important thing is that to open up the data, because the data is not an information, but it's also an opportunity for the students, even if in the schools or in the college, before they formally enter into this research business. So it is a huge opportunity for the students to get into this database when with the help of their teachers and their professors sitting in their school or colleges, and to help the research community far beginning before the former PhD and so on. So I think this meeting and this panel gave us a very excellent idea about this utilization of this opportunity, and I thank all of them for making this event very, very successful. Thank you very much. This is the time for asking questions. All the dignity speakers are here. So please, if you have any questions, please start. Yeah, please. Can someone give a mic to this person? Yes.
Thank you, sir. I am Dr. V.K. Mishra from Atal Bihari Vajpayee Hindi University, Bhopal. I am working in solar activity, space weather, and cosmic ray modulation. So naturally, I am interested in Adit L1 mission data. Today, which we are seeing that we have only some event-based data provided by Adit L1 through some portal of ISRO. Can we have a continuous series of hourly data of interplanetary medium, solar wind velocity, density, temperature, which we are nowadays using from OmniWeb service? That kind of data we are able to achieve from Adit L1, and if not, then for how much time we will able to get it?
Yeah. So Aditya L1 data in the Pradhan platform is there actually the full data. It's not event based. Have you registered in Pradhan? So in Pradhan, whatever observations have happened, all the data is available. So initial period, there is some verification phase. So there will be certain test data and all that. That may not be available because you will not be able to use it also, because those are very different type of test data. These are not science ready data. But when the regular science observation has started, all the data is available. There are certain times, it's not that all the 7 payloads are observing all the time. That also you have to realize that. These are observatory class mission. So there will be certain occasions when all the data, all the 7 instruments will have some data, but there will be periods on which some particular instrument is doing some, again, calibration studies. So that data will not be available. But if you are not finding out any particular dates and time data, you can write to the Pradhan. There is a help desk also. Yeah, it is there for, say, for example, the in situ data is available. Magnetometer data is continuously available. X-ray data is also continuously available. But the 2 remote sensing, primarily the SOOT instrument and the coronagraph instrument, they are more in a, very specific modes of observation is available. Having said that, SOOT data is also now available at certain levels of data and all that. So if you do not find certain data, please write to, the Pradhan website also you can write. Otherwise, you can write to us also. We will connect you with the right people. Yeah.
I am Gupta from ISRO. My question is to Dr. Bharadwaj. You mentioned that in a 10 centimeter thick layer, we have found the temperature difference of 40 Kelvin. So I feel it will be a very hopeful observation. Can you tell what are the conclusions we can draw from that?
So what it means actually is that the moon surface is highly non-conducting. Thermal conductivity is of the order of 0.002, 3 kind of things. which in turn means that heat is not propagating from the surface down. Now, one of the ways in which we are all thinking that we have to go to the poles to look for water. Now, our study has shown that you can look for water at mid and high latitudes also, because heat is not going down. So if there are pockets of ices, it can be retained there. In fact, there is a simulation paper which we have done more recently, where we showed that at 70 degrees south, where we landed the Shiv Shakti point, if you go almost like half meter deep at that landing sites, we can have water. So these are very important implications which was not known. We were all thinking that we have to go to permanently shadowed regions or at higher latitudes to look for waters. So these are huge implications for current science. If you look in the future in terms of human habitation, you can use this regolith for safeguarding the humans or using as a blanket for human settlements, because it is not conducting. So since there is no atmosphere on the moon, you are directly exposed, you can actually use as a thermal blanket.
We are already running out of time, so we can take one last questions to close before closing the session. Yeah.
Sir, this question is related to Professor Dipankar and also Professor Bharadwaj's work. As we know, currently we have very few solar missions working in the orbit. Like Sir Parker की बात करें या आदित्य एल1 की, तो क्या हम internationally एक दूसरे से collaboratively data share करते हैं, sir, rather than publications, so that we have a wider scope of understanding about our own sun? And secondly, sir, as you were talking, Bharadwaj sir, कि 10 centimeter 50 Kelvin का जो difference है, as Gupta sir has also mentioned, तो जो human habitat का जो plan है, even NASA का जो Artemis series का plan है, तो in future, तो हम जो solar radiation safety के लिए astronauts के लिए, तो कितना viable लगता है आपको ये projects in terms of future exploration as far as financial investments are concerned?
Okay, I will start on the bottom, the last one. See, Artemis mission currently is for human exploration of the moon. So basically humans going to the moon after half a century. India is also planning, I have already told about that. 10 centimeter temperature difference of almost 50 Kelvin and so is to be utilized by everybody. It is not for India alone. India has found out, but it is known to the whole world now because of the publications which we do in international reputed journals. In terms of this information for human settlement, it is largely for thermal blanketing. But if you want to use this also as a radiation blanket, you can automatically do that because both are synonymous to each other. If you have a brick of almost like 9 inch or 9 centimeters and similar thick, it will also reduce the load of the radiation in terms of the particles, which was also talked about by Dipankar and Tarun, that charged particles come from the sun at all point of time, in particularly the solar energetic charged particles, which have energies of MeVs kind of things. So it is useful for both ways. And for the other question, I will give it.
Yeah, so the joint collaborations is happening very, very regularly. In fact, in Aditya, now there is a proposal mode available. So anybody throughout India can submit a proposal. And 10% global, it's not yet open. But if you have a international collaborations, foreigners can also participate. So 10% of the Aditya time is now reserved for joint observing campaign, 10% of the observing time. And from the very beginning for cross calibrations and all that, many instruments are also having, joint observations. For example, SUD, they have, joint campaign with some of the NASA missions. Solar Orbiter has already done some, joint observations. Prova 3, we have some joint observing campaign. So there are, I was just seeing some results my student has sent just half an hour back from Prabha. And we are going to look at from Aditya spectrograph also. So there are definite, joint observing campaigns happening. And internationally, it is now very much encouraged to have joint observation. Yeah, so Aspects also has done some experiment with one of the instruments from a solar orbiter.
Oh, okay. Thank you so much. Thank you all the eminent speakers. So we are now officially closing the sessions and we have an high tea. So if you have more questions, you can interact with the speakers there. Okay. So they have some other announcements. Thank you.
Thank you.
मैं आदरणीय डॉक्टर शिव कुमार शर्मा जी, राष्ट्रीय ऑर्गेनाइजिंग सेक्रेटरी विज्ञान भारती से अनुरोध करूंगा कि हमारे प्रतिष्ठित वक्ताओं को अंगवस्त्र, श्रीफल एवं स्मृति चिन्ह भेंट करने हेतु मंच पर पधारें।
प्रोग्राम क्या क्या होंगे?
हाँ, वो मैं
इसके बाद हाईटी है, हाईटी का कार्यक्रम साढ़े 6 से म्यूजिक का प्रोग्राम, अभी म्यूजिक का प्रोग्राम 8:30 बजे ऐसे रवानगी, ऐसा बोलते ना ये हेलो
आप सभी का बहुत बहुत धन्यवाद। द फ्यूचर ऑफ एस्ट्रोनॉमी एंड स्पेस रिसर्च इंडिया सत्र में अंतरिक्ष की दिशा में हो रहे क्रांतिकारी अनुसंधानों पर आधारित प्रस्तुति के लिए सभी वक्ताओं का हार्दिक आभार। यह सत्र भारत की अंतरिक्ष अन्वेषण, उपग्रह प्रौद्योगिकी और खगोलीय विज्ञान में हो रही नई उपलब्धियों को समझने में मददगार रहा। मैं इस ज्ञानवर्धक सत्र को साझा करने के लिए वक्ताओं को धन्यवाद देता हूं। साथ ही सभा में उपस्थित प्रबुद्धजनों, विद्वानों का भी सादर धन्यवाद ज्ञापित करता हूं।
बोल दीजिए हाईटी
धन्यवाद। अभी जस्ट यहाँ हाईटी है, जो हाईटी आपको जस्ट इस तरफ है, जो हाल में उपस्थित हैं उनके लिए राइट साइड में है। और उसके बाद जो है 6:30 बजे से कल्चरल एक्टिविटी है, जिसमें महाकाल ड्रम बाई 50 आर्टिस्ट ग्रुप फ्रॉम भोपाल की प्रस्तुति है और ताल फ्राई अभंग नाद ग्रुप फ्रॉम दिल्ली की प्रस्तुति है। और तत्पश्चात भोजन के उपरांत 8:30 बजे बसेस के लिए प्रस्थान करेंगे और अपने अपने
ठीक है। आई एम रिपीटिंग कि यहाँ अभी हम लोगों की एक हाईटी है राइट साइड में, और इसके बाद में हम जस्ट 15 मिनट बाद हमारा म्यूजिकल प्रोग्राम शुरू होगा, और आफ्टर स्टार्टिंग ऑफ म्यूजिकल प्रोग्राम 1 आवर हमारा डिनर शुरू हो जाएगा 8:30 शार्प, यानी मैक्सिमम 8:30 वी विल बी लीविंग यहाँ फ्रॉम हियर। हाँ, यहाँ नाइट स्काई गेजिंग का भी अरेंजमेंट्स किया गया है, तो जो इंटरेस्टेड हैं वो ये कर सकते हैं इस एक्टिविटी को।